Hello, everyone. It's Billy Younger again for Billy Younger's PhysicsSolutions.com or just PhysicsSolutions.com. I'm here to solve another Coulomb's law problem. This is just continuous of the previous one. The previous one was to calculate the force on a charge capital Q over the center of an electric dipole that had a charge of one negative charge that was Q1 equals negative 1.11 nanocoulombs, and Q2 was positive 1.11 nanocoulombs, and they were basically 6 centimeters apart. And then above the center of that 6 centimeters was a 4 centimeter distant charge capital Q. Now we've moved the capital charge capital Q from the center above the dipole to above the negative charge, and we're going to do the same calculation again. Later, we're going to do this calculation using the electric field instead of calculating the force first and then calculate the force. We're going to do it for both the previous problem that I just finished working, which is where the capital Q was above the center, and the one that I'm getting ready to work now, which is with capital Q above the negative charge. So let's go ahead and get started. I'm going to share my iPad screen with you guys. So here's the iPad screen, and I've got the problem already written on it. So you'll be able to see the diagram as well as the actual problem. So if you'll notice, here's our little electric dipole. Remember, electric dipole is basically two equal magnitude charges, one positive and one negative. And since it's only 2 points, they obviously have to form a straight line. And then the electric dipole is represented basically by those two charges. And we represent it with a vector P that's equal to the magnitude of the charge, which in this case would be 1.11 times 10 to the negative 9th coulombs, times the distance between them, which in this case would be 0.006 centimeters. So if you multiplied 0.006 meters, since it's actually converting it to meters, if you multiplied 0.006 times 1.11 times 10 to the negative 9, then you get the actual magnitude of the electric dipole. So in this case, we actually have the plus Q, the positive Q charge up above the negative charge, and I'm asking what is the total force on the charge Q in the diagram. So I'm going to start off by writing solution. And to make this work, we have to, of course, understand how forces behave, and they are behaving like vectors. So the total force on charge Q, I'll just call FQ. But what this means is the total force FQ is the force on Q due to charge Q1, which I'll call FQ1, plus the force on Q due to charge lowercase q2, which I'm going to call FQ2. So that's how I work that. Of course, that also means that FQ sub x is equal to FQ1x plus FQ2x, and FQy, the y component of the total force FQ, is FQ1y plus FQ2y. So that's what we got to work out. Of course, Coulomb's law gives us the magnitude of that force is K QQ over R squared, where R is the distance between the point charges Q and capital Q and lowercase q. In this case, they're both point charges, so that's perfectly understandable. If it wasn't point charges, then we'd have to find the center of charge of the two charges, connect the line to them, and the force would act along that line. And the distance between them, of course, would be the distance between those two centers of mass. So that's just part of what we're trying to do here. So let's just start beginning. Let's start with calculating the force on Q due to lowercase q1. Notice how I'm going to leave off the actual charges, the actual sign of the charges, times 10 to the 9th. That's Newton meters squared per Coulomb squared. That's the units of K. And then, of course, the lowercase q is going to be 1.11 times 10 to the negative 9th, because nano is 10 to the negative 9th. And then the capital Q is 1.00 times 10 to the negative third coulombs. And we're doing Q1 here, so the distance between them is exactly 4 centimeters. So I'll say 4.00 times 10 to the negative 2 meters, and that's going to be squared. Now, when I do this calculation, I get 8.998 times 10 to the ninth times 1.11 times 10 to the negative 9 times 1 times 10 to the negative 3. All that's going to be divided by, in this case, it's going to be, I'll go ahead and do a parentheses, 4 times 10 to the negative 2. So, and then I got to square that distance. And that gives me 6.2424. And as always, I'm keeping 2 extra sig figs, or as almost always keep at least 1 extra sig fig. A lot of times I keep 2. So that's the magnitude of the force between Q1 and capital Q. Now, capital Q is a positive charge, and lowercase q1 is a negative charge. So Q1 and Q actually attract one another. So the force on capital Q would actually tend to make capital Q move down towards negative Q. So I'm going to say this force is actually acting this way. That's going to be my negative y direction. And that's going to be just plain FQ1. Okay. Now, I haven't really done anything in terms of coordinates, so I am going to have to break it down into x and y components. So I'm going to call this as the positive x-axis pointing to the right. I'm going to call this the origin. I'm going to call this the positive y-axis pointing up. And of course, this would be the negative axis pointing to the left. Now that I have FQ1, I'm going to go ahead and compute the x and y components, which is really trivial because this is clearly a vector that points only downward. So I'm going to say F. Actually, let me go ahead and separate the diagram from the solution so it looks a little less confusing. Okay, so that's basically the diagram. So now I'm going to say FQ1 sub x is actually equal to 0 because it points straight down. There's no x components. FQ1 y is actually going to be negative 6.2424 newtons. And again, that's negative, just refers to it pointing downward. So that should be fairly straightforward. Now we're going to go ahead and calculate FQ2, and that's going to be 8.998 times 10 to the ninth newtons meters squared per coulomb squared. That's going to be times the lowercase q, which is 1.11 times 10 to the negative 9 coulombs, because it's nanocoulombs. And the capital Q is 1.00 times 10 to the negative 3 coulombs, because that was in millicoulombs. Now there's a bit of a problem. Specifically, the distance is no longer a trivial thing to get because it doesn't happen to be a actual, that didn't turn out so well. It does not happen to be an actual special 3-4-5 triangle. It's this triangle, which is evidently 6-4. So it's got 6 centimeters as the horizontal leg, and it's got 4 centimeters as the vertical leg. And that, of course, allows us to get I get a different angle, of course. I can work all that out, but right now I just got to figure out what the actual distance between the two charges are. So using the Pythagorean theorem, I can go ahead and underline this. And I got to remember the distance has to be squared. So we'd normally find the square root of the sum of the squares, and that would give you the distance. But we want it squared, so I'm just going to leave the square root off. I'm going to say the distance is 6.00 times 10 to the negative 2 meters. That quantity is going to be squared because that's the horizontal leg of the triangle, plus 4.00 times 10 to the negative 2 meters. Again, that one's going to be squared because that's the vertical leg of it. And like I said, normally we'd take the square root of that, but since we're squaring it, why bother? So I'm going to take 8.998 times 10 to the ninth times 1.11 times 10 to the negative ninth times 1 times 10 to the negative 3. Now I'm going to divide all that. This time it's really helpful to use parentheses. And I'm going to say 6.00 times 10 to the negative 2 squared plus 4.00 times 10 to the negative 2 squared, close parentheses, and this gives me a force of 1.90, or excuse me, 1.92. And then that's all the sig figs I'm supposed to have. I want to carry 2 extras, so that's 0.7 newtons. That's the total force. Now, we might notice that this distance is quite a bit more than 4, and we would have, of course, expected this force to be smaller, and this definitely says it is smaller. You could, in principle, find out what that length is, compare the ratio, compare the squares of the ratio of the squares, and you'd see exactly what factor it's off by. But that's not that terribly important right now. So what we do know is the charge Q, capital Q, is positive, and the charge lowercase q2 is also positive. So this is a repulsive force, and I'm going to say it's going to act right along the diagonal of this triangle, and it points that way because you might think of capital Q as being compelled to move away from lowercase q2. This helps to actually figure out what this triangle is. For instance, I'm going to say this is 6.00 centimeters, and this is 4.00 centimeters, and this is the angle phi, say, and phi is equal to the tangent inverse of opposite over hypotenuse, so that's 4/6. And I'm going to use 4 sig figs just to be safe, so I'll say tangent inverse parentheses 4 divided by 6 close parentheses. This gives me 33.69 degrees. So that means this angle right here is 33.69 degrees. And of course, we can break this down into a negative x component, which would be like this. And then it's going to make a positive y component like that. So that's what we got to work out now. I'm going to adopt the signs by that configuration that I just looked at. So I looked at it. I noticed that in order to move from the tail of this vector to the head, if I wanted to go parallel to the axes, then I'd either go up along the y-axis first, which means a positive y component, and then left along the x-axis, which means a negative x component. Or I could do it the other way and say, go left along the x-axis, that's a negative x component, and then up along the y-axis, that's a positive y component. So you see, I get the same signs either way. Now I'm going to use that sign convention, or that sign that I just decided, by saying that FQ2 sub x is going to be, remember this angle is 33.69 degrees, and of course the x component is adjacent to that angle, so I'm going to use cosine this time. So the answer is going to be negative 1.9207 newtons times cosine 33.69 degrees. So I'm going to say 1.9207 times cosine 33.69 is equal to, remembering my negative sign, that's going to be equal to negative 1.5981 newtons, again carrying two extra sig figs. And now I can calculate the y component, FQ2y. That's going to be positive, so I'm going to force that sign right here, 1.9207. Now we see that the y component is the blue one, and that is opposite the 33.69 degrees. So sine equals opposite over hypotenuse. So we're going to use the sine of 33.69 degrees. This will give us positive 1.9207 times sine 33.69. That gives me 1.0654 newtons for the y component. So the FQ sub x is the total resultant force component in the x direction. So I have to add the two x's, which is 0 plus negative 1.5981 newtons. So this is going to be negative 1.5981 newtons. FQ sub y is going to be the sum of the two as well. In this case, the y component for one was negative 6 point. I can write that better than that. Come on now. So it's negative 6.2424 newtons. And then I've got to add it to the other y component, which is positive 1.0654 newtons. And that's going to give me negative 6.2424 plus 1.0654. Looks like all my numbers are working. That gives me a negative 5.177. And again, keeping two extra sig figs, I'm going to write 70 with a line under it. So now I have the x component and the y component, and I can draw my axes again. Notice in this case, I have an x component that's negative and a y component that's negative. So really the bottom left quadrant is what I care about. So if I draw this to be my positive y component and this to be my positive x coordinate axis, that's what I should have said the other time, then I can basically say that about 1.5 is the x component. And of course, that's in the negative direction. So what I'm going to do is draw that like this, and that's 1.5981 newtons. And then in addition to that, I have negative 5, which is quite a bit bigger than this one. This is going to be 5.1770 this way. And these two are, of course, at a right angle. And that means the net vector is this. So that's FQ is that vector right there. And this angle phi we'll have to figure out. We can use the Pythagorean theorem to get FQ. So FQ is going to equal the square root of 1.5981 newtons squared. A little bit of complexity when you're adding or subtracting sig figs, so keep an eye on that. And then 5.1770 newtons, again squared, So when I add, when I square 1.5981, when I square that, I get 2.5539. So that's only good to the, using 3 sig figs, that's only good to the hundredths place. So it's 2.5539. When I do the other one, 5.1770, again, supposed to be good to 2 sig or 3 sig figs. When I square that, I get 26.801. Since that's 26, in other words, bigger than 9, that means 2 of my sig figs are used to the left of the decimal, which means the addition is only good to the tenths place instead of the hundredths place. So now I've got to add the 26.801, which was what 5.177 squared was. I've got to add that to the 2.55392361, which is what the other number was. And I just got to remember to round it to the hundredths place. So, or excuse me, to the tenths place. So when I added those two together, I roughly got 29.355. And now I got to take the square root of that. So the square root of 29.355 is equal to 5.41. I'll carry 2 extra sig figs. In fact, this one, once I finally added those, I got 29.3. So that was 3 sig figs. I'm raising this to a power, so I get out 3 sig figs. So now I'm good to the nearest hundredths again. So I do got 3 sig figs again. I'm going to add these extra 2 digits just in case I need them. And that's the magnitude of the vector. Now phi is equal to the tangent inverse of the opposite side, which would be 5.1770 over the adjacent side, which is 1.5981. So when I do that, I'm going to say tangent inverse 5.177 divided by 1.5981, and that spits out 72.84. I'll carry 1 extra digit. That's going to be 5. I'll carry 2. Actually, no, I've already got 1 there, so I'll call this next digit just a 5, and that's degrees. And obviously, I'm carrying it too far. So what we now have is the total force F Q. We can write it a couple different ways. Actually, I'm going to start writing it further to the left. So let me erase that and write it further to the left. I'm now going to say FQ as a vector. Well, that's not looking really good the way I drew that. So let me blow it up and make it so I can write it a little easier. So FQ as a vector is going to be, I can go ahead and write it with I hats, J hats, and K hats, or X hats and Y hats. I'm going to go ahead and do that, at least for the calculus-based students, so they'll see what it is. In this case, we've got the X component is a negative 1.5981 newtons times I hat plus negative 5.1770 newtons J hat. So that's one way of writing it. But the other way of writing it that is a little more easy to use, 5.4180 newtons. And this is going to be at, notice if I went counterclockwise from the positive x-axis to the negative x-axis, that'd be 180 degrees. I've got to add another 72 to that. So this one's going to be 152, 150, or excuse me, 180 plus 72. Sorry about that. So 180 plus 72 would be 252.845 degrees. And of course, the 4 and the 5 are not sig figs. So that's our total answer there for the total force Q when F on total, the total force on F capital Q Exactly. Yeah. So the total force on charge capital Q is called F sub Q, and it's written in those two possible ways. And hopefully that helps you. I'm going to go ahead and call it a day. And I will do two more videos in which I do the same thing as I did on this one and the previous one. Only this one, there's the two videos that I have left. I'm going to calculate the electric field first, and then use the equation to find the force on it from the results that I got from the previous problem. So let's go ahead and say goodbye. Bye-bye, everybody. I'm going to stop sharing now, and then I'm going to say bye-bye.